Hello everyone, welcome to another kinetic tutoring episode. Today we have another simple harmonic motion video, but this time instead of talking about a simple pendulum, we're going to be talking about the harmonic motion of a spring. So let's get right into the problem. Prompt reads, a mass of 500 grams on the end of a spring is observed to move back and forth with a frequency of 2 Hz. During this motion, its maximum speed is 4 meters per second. Part A is asking us to determine the spring constant K, and Part B is asking us to find the amplitude of the oscillation. So let's get started with Part A. So one of the things we know we're going to need to use is the force, the restoring force of a spring, which we know to be Kx. And K is going to be the spring constant, while X is going to be the displacement of the spring. And we know that the notation for force is simply mass times acceleration. And what we want to do here is get an equation for acceleration. So we'll just simply divide both sides by m to get that our acceleration is K over mx. And in order to solve for our K here, we're going to have to find another equation for acceleration. And the way we can do this is to find a equation for the spring's displacement and then take 2 derivatives in order to find the acceleration equation. So let's draw a diagram of this spring. Here we have a wall that our spring is going to be attached to. There's going to be a mass at the end of the wall, at the end of the spring, and it's going to be oscillating from a point negative A to a point A over here, and this point here will be 0. So let's write an equation for this, and the way we're going to do this is by using a sine or cosine graph. It doesn't really matter, it just depends on where the box is starting. Let's use a cosine in this example. So we'll write that the displacement in terms of time is A cosine of omega t. This is just our standard equation for displacement. And let's solve for acceleration. So let's take 2 derivatives of this function here. Our v of t is going to be negative a sine omega t times the derivative of the inside, which is omega. And our acceleration is just another derivative of this, negative a cosine omega t times another derivative of the inside, which will give us another omega, so we'll have omega squared here. So what we can do here is we find that we have an a cosine omega t down here and up here, and we know that this a cosine omega t is simply displacement. So we can just set this a cosine omega t as x. So let's rewrite our acceleration as negative omega squared x. All we did here was just substitute this term for this term right here. And now let's set our 2 equations equal to each other. We have K over mx is equal to omega squared x. You might be wondering why I got rid of the negative sign. That's because the negative doesn't really matter too much in this case, because when it's oscillating, it doesn't really have a specific direction that it's going to be going in the entire time. It's just kind of moving back and forth. And we can get rid of our x's here, and we'll find that K over m is omega squared. And since we're solving for K, our K is going to be m omega squared. I'm going to erase this page to free up some more space. Alright, let's rewrite our equation. Now, we're given mass, but we still have to find out what our omega is going to be. So we can use this information we're given here. Our frequency is 2 Hz, and we know that omega is simply 2 pi over t where t is our period, or it can also be written as simply 2 pi frequency. So let's plug in our frequency of 2 here, and we'll just get that omega is going to be 4 pi. And now that we have this value of pi, we can simply plug that into our k equals mw squared. Get that k is equal to 1/2 in terms of kilograms, because we have 500 grams, which is going to be half a kilogram, times 4 pi squared. 4 pi squared is simply 16 pi squared when we distribute, and that times 1/2 is going to give us 8 pi to the power of 2. And that will be our answer for part 1. Our k is going to be 8 pi squared. Now let's move to part B. Find the amplitude of its oscillation. And the crucial information that we're given here is the max speed, 4 meters per second. This is going to be how we're going to find our amplitude. So if we look back at our displacement function, x of t was a sine or cosine omega t. And we know that our omega is 4 pi. So x of t is simply a cosine 4 pi t. And from here, since we're given the maximum speed, which is just maximum velocity, let's take a derivative to get our velocity equation. So the velocity equation is going to be v of t is negative a 4 pi sine 4 pi t. And we know that this is going to be a maximum when sine of 4 pi t is at -1, because we know that the range of sine is just from -1 to 1. And since there's already a negative in the front, we want the two negatives to cancel out. So we want the greatest negative number, which is going to be -1. Let's plug that in. So we get -1, negative a 4 pi is equal to our v max, which is 4. And then from here, let's write this out. We'll get a 4 pi. And from here, all we're going to do is divide both sides by 4 pi, and we'll get that a is 4 over 4 pi, which we can just simply write as 1 over pi. And there you have it. That's how you go about solving this problem. I hope this helped, and make sure to tune in later for more physics tutorials.